Welcome to the channel Professor Davinci. Binary search tree, in short we can say BST, is a hierarchical data structure composed of nodes where each node contains a value and has at most two children, referred as left child and right child. So BST is a hierarchical data structure. It is a, we can say this is a hierarchical data structure. It consists of at most two children. One is called a left child and a right child. It is similar to the binary tree, but the only difference is the key property. So what is the key property? Key properties. The first property is all value in the left subtree or less than the value in the node, that is root node, or we can say parent node. This is our first property. And second property is all the value in the right child not right child, right subtree or greater than the value in the root node, or you can say parent node. So these are the very important property of a binary search tree. This property allow for efficient searching, insertion and deletion. So these two property, in short I can say these two property, in short I can say the left child is less than the parent and the right child is greater than the parent. For example, I draw a single tree, okay, single small tree. Suppose this is 5, okay. The left side of the tree must be less than the parent. So parent of 5, this must be less than, and the right side must be greater than the maybe 8 or 9, whatever. Okay, so this is, but in normal binary tree, this is not the case. We can have like this, we can have like this, or we can have like this. Okay, so this is the binary tree, but in the binary, this is the BST, binary search tree. Always, because this search tree, always the left child must be less than the parent, this is the parent, and the right child must be greater than the parent. Okay, now for example, if I take a very large one, I change the color, so I have a tree 10. Okay, so it has two trees. So left tree say maybe less than 10, and right child must be any value greater than 10. So this 5 have again another subtree, it has less than 5, say greater than 5, and less than 3 and greater than 3, less than 7 and greater than 7, and less than 13 and greater than 14. So if we say the first property, what is the first property? The left subtree must be less than. So if we take this left subtree, what is the left subtree of 10? For example, this is a left subtree. If we check all the values say 5, 3, 7, 2, 4, always less than the parent node, that is a root node. If we take the right subtree, this is the right subtree. Okay, right subtree always greater than the parent, that is greater than the root 10. So 13, 11, 14 always greater. Not only this, any subtree, I erase this one. For example, if we take this subtree, okay, if we take this subtree always less than 5, okay, because for this subtree, who is the root node? 5 is the root node, I mean the parent. See here that 3, 2, 4 always less than 5, and also similarly if we take the right subtree of 5, it is greater than 5, 7, 6, 8. Okay, similarly here if we take 11 is less than 13 and 14 is greater than 13. So this is a very much important property where it is very special. So BST is a special tree. So what is the speciality? So the speciality of a binary search tree. The specialty binary search tree is the in order traversal. Already we have seen in order, pre-order, post-order traversal in the last video. So in binary search tree, the in order traversal is always sorted. For example, I can take this one. For example, I can take this one. Okay, this one. So 5, 4, 8. For example, I take this one. 5, 4, 8. What is the in order representation of a BST? So in order means parents should be in between, left side, right side. Post order, parent at the last, left child, right child. Then pre-order, parent is first and the left child and the right child. Okay, so we are not concerned about post order or the pre-order. Always concerned the specialty of the in order representation or in order traversal of a binary search tree is always sorted. Sorted means what? In maybe in ascending order. See here, 4, 5 and 8 always sorted. Always sorted in ascending order. Okay, so this is a very much important property of a binary search tree. If you make this in order traversal for this big tree, I erase this one, this change the color. Okay, good. So I can represent in order for this tree, in order. So 10 in the middle, 5 this side, 13 that side, and for this 5, 3 this side, and 7 this side. For 2, 4, for 7 is 6 and 8, and for 13, 11 and 14. If you see here, this one in order traversal of this BST, see the in order representation of a BST always sorted. So it holds us 2, 3, 4, 5, 6, 7, 8, 10, 13, 14, 11, 13, 14. Okay, this is a very important property, specialty of the binary search tree. Based on this specialty, there are many algorithms we can perform. So what is the algorithm? So we can perform searching, and we can perform insertion, and we can perform deletion. So these are the algorithm we use in this one. In this, among this insertion and deletion, this binary search tree mainly considered for the searching technique. Still, in a large database, we are using BST to search the element. So okay, so while implementing the database, we need to implement the data representing the binary search tree. So in this case, the searching is very easy because suppose if I want to search 7, so what first go to compare the root node 10. So 7 is the less than 10. That means 7 will not be available on the right side. Of course, it's available only on the left side. So we go for the searching the next subtree, left subtree. 7 is greater than 5, so that means 7 is not available on the left side. 7 is available on the right side. So we go here. Yes, we found the target. Oh, sorry, we found the target. So meaning the search area is narrowed. Based on the root node. We can suppose I have 10 million elements. If I want to search for a particular term, so based on the root node, I can ignore 5 million this side and 5 million that side, right? So based on the search value compared with the root node, I can ignore any one of the side, either 5 million of the left side or 5 million, I mean say 0.5, not 5 million, yes, 5 million. This side 5 million I can ignore, or that side 5 million I can ignore, because 7 or the search element available either left side or the right side based on the root node. Clear? If the root node is less than 7, that means I can ignore completely on the left hand side of the tree. That is 5 million element I can ignore, no need to search for. So in this case, this is very efficient. Binary search tree is efficient for searching technique. So clear? So this is all about binary search tree. See you guys. Have a great day.